Foundations of Computational Theory. A deep dive into core principles. Computer science is the study of principles and methods behind digital computation, encompassing everything from hardware architecture to algorithmic logic. At its heart lies a blend of mathematical rigor and engineering ingenuity, enabling humanity to solve increasingly complex problems through code. This article explores the theoretical pillars that define computer science, offering insights into algorithms, computational complexity, and abstract models of computation. Whether you're refining your coding skills or diving deeper into the math behind programming, these concepts form the bedrock of innovation in technology today. The essence of algorithms in computation. An algorithm is a precise sequence of steps designed to solve a specific problem or perform a particular task. From sorting numbers to routing internet traffic, algorithms power nearly every digital interaction we experience daily. At their core, algorithms embody logical decision-making processes encoded in a way that computers can execute unambiguously. Efficient algorithms minimize resource usage, ensuring tasks complete quickly even with vast inputs. Understanding algorithm design patterns, from greedy approaches to divide-and-conquer strategies, is critical for optimizing software performance. For instance, quicksort leverages partitioning to sort elements in average case logarithmic time, $O, n/log n, $. The choice of algorithm profoundly affects system behavior. While bubble sort has $O, n², worst case runtime, merge sort guarantees $O, n/log n, efficiency regardless of input order. Deterministic versus non-deterministic ***. Deterministic algorithms follow fixed rules, producing predictable outputs. Non-deterministic ones may explore multiple possibilities simultaneously, often analyzed theoretically via complexity classes. Creativity in design ***. Developing novel algorithms requires creativity akin to mathematics, balancing correctness, efficiency, and adaptability to new problem domains. Computational complexity. Measuring algorithm efficiency. Computational complexity quantifies the resources required by an algorithm, primarily time and memory, as functions of input size. This analysis guides decisions about feasibility and scalability in software development. Time complexity classifies algorithms based on growth rates. Polynomial time algorithms, $p$, like those with $O, n², runtimes, generally outperform exponential time counterparts, $np$ complete problems, for large datasets. The importance of asymptotic analysis. Asymptotic notation simplifies comparisons between algorithms by focusing on dominant factors. Big SOS, $\omega$, and $\theta$ notations describe upper bounds, lower bounds, and tight bounds respectively. For example, an algorithm with $O, constant time executes identically regardless of input size, whereas a logarithmic $O\log n, algorithm grows slowly relative to linear $O, n, alternatives. Real-world optimizations often hinge on reducing asymptotic complexity. Replacing nested loops with hash tables can transform quadratic $O, n², operations into near-linear $O, n, performance. Data structures. Enabling efficient algorithm execution. Data structures organize data to optimize specific operations like searching, inserting, or deleting elements. Choosing the right structure can dramatically reduce algorithmic overhead and improve system responsiveness. Arrays offer fast random access capabilities but require contiguous memory allocation, limiting flexibility during dynamic resizing. Linked lists, in contrast, allow efficient insertions/deletions at arbitrary positions but sacrifice direct element access. Trees and graphs model hierarchical relationships and connections between entities. Binary search trees enable ordered traversal with $O\log n, search times when balanced, while adjacency matrices represent graph edges compactly. Hash tables leverage hashing functions to map keys to indices, achieving average case constant time, $O, $lookups and insertions. However, Collisions necessitate careful resolution strategies like chaining or open addressing. BST versus AVL trees ***. Balanced binary search trees maintain height balance, ensuring $O\log n operation times compared to potentially $O n degenerate cases in standard BSTs. Graph traversal techniques ***. Depth first search DFS explores paths recursively, while breadth first search BFS systematically examines nodes level by level, each suited for distinct application scenarios. Automata theory, modeling fundamental computing concepts. Finite automata serve as simple computational models capable of recognizing patterned strings. Their deterministic and non-deterministic variants underpin lexical analysis in compilers and regex engines. A deterministic finite automaton, DFA, transitions deterministically between states upon reading input symbols, forming the basis for scanners in programming languages. Non-deterministic versions, NFA, relax transition uniqueness, enabling expressive pattern matching capabilities. Push-down automata extend DFAs with stacks, allowing recognition of context-free languages, a requirement for parsing arithmetic expressions and programming constructs involving nested structures. Turing machines constitute the theoretical foundation of general-purpose computation. Despite their simplicity, they encapsulate all solvable problems, establishing boundaries for what is computationally possible. Limits of automata-based computations. Not all problems can be solved by finite automata. Regular expressions, corresponding to regular languages, cannot handle inherently recursive structures requiring unlimited memory. Context-sensitive grammars demand more powerful models like linear-bounded automata. These fall outside push-down automata capabilities due to memory limitations imposed by stack-based architectures. Turing completeness defines whether a system can simulate any Turing machine. Programming languages like Python and Java achieve this status, enabling universal computation through conditional branching and loops. Computability theory, defining what can be solved. Computability theory investigates whether problems admit algorithmic solutions. Central to this field is the distinction between decidable and undecidable problems, shaping our understanding of algorithmic limits. A problem is decidable if there exists an algorithm that always halts and produces correct answers. Classic examples include checking primality or verifying propositional logic formulas. In contrast, undecidable problems lack effective procedures guaranteeing termination. The halting problem exemplifies this, demonstrating that no program can determine whether another will eventually stop running. Reduction techniques prove problem equivalences. If problem X reduces to Y and Y is unsolvable, then X must also be unsolvable, an approach used to classify numerous undecidable questions in mathematics and computer science. Complexity classes, categorizing algorithm difficulty. Complexity classes categorize problems based on solution difficulty, distinguishing tractable from intractable challenges. Classifying problems into these categories informs practical algorithm selection and approximation strategies. $P$ represents decision problems solvable in polynomial time, implying efficient solutions exist for these instances. Examples include determining connectivity in graphs or checking numerical properties like divisibility. $NP$ encompasses problems verifiable in polynomial time. Many cryptographic protocols rely on $NP$ complete problems presumed hardness, assuming $P\NEC NP$. However, this remains one of mathematics' greatest unresolved conjectures. $NP$ completeness denotes hardest problems in $NP$. Finding a polynomial time solution for any such problem would imply $P equals NP$. SAT, Boolean satisfiability, serves as archetypal $NP$ complete problem with wide-ranging implications. Formal languages and grammars, structuring information. Formal languages define sets of valid string representations governed by syntactic rules. Chomsky hierarchy classifies languages based on generative grammar types, influencing compiler construction and parser design. Type 3 grammars produce regular languages recognized by finite automata. These correspond to patterns expressible via regular expressions found in text processing utilities and lexical analyzers. Type 2 grammars yield context-free languages parsed by pushdown automata. Most programming languages employ BNF-style productions reflecting these grammatical structures. Type 1 grammars permit context-sensitive productions, requiring memory proportional to input length. Linear bounded automata recognize these languages, although implementing parsers proves challenging due to increased complexity. Type 0 grammars represent unrestricted languages recognized by Turing machines. These capture all computable sequences, including many esoteric or highly structured formats encountered in specialized domains. Emerging trends and theoretical foundations. Quantum computing redefines traditional notions of computation through qubit superposition and entanglement. Quantum algorithms promise exponential speedups for certain problems like integer factorization and database searches. Approximation algorithms address optimization problems lacking exact polynomial time solutions. Techniques like randomized rounding or local search find near-optimal results while maintaining tractability. Online algorithms process requests sequentially without prior knowledge of future inputs. Competitive analysis evaluates their performance against optimal offline counterparts, informing designs for caching and scheduling systems. Distributed computing extends single machine paradigms to networks of interconnected processors. Consensus algorithms and fault tolerance mechanisms become crucial for reliable coordination among distributed components. Conclusion: theoretical computer science forms the intellectual scaffolding supporting modern technological innovations. By mastering algorithmic principles, complexity hierarchies, and formal models, programmers gain unparalleled insight into building robust, scalable systems. Whether debugging inefficiencies in existing codebases or designing novel solutions to emerging challenges, grounding oneself in these foundational concepts equips practitioners to navigate ever-evolving landscapes of software development and computational theory.